wanted to try and do something awesome with the app and create a poll out of it, but it doesn't seem to work as well. So we're going to go old school and just do a raise of hands. So how many of you are not familiar with traps at all, haven't heard about it that much, haven't tried it? OK. How many of you have tried traps or seen it, heard about it, but not actively using it? OK, last, that's good. And for those of you who are using traps, who is using the latest and greatest 5.0? Awesome, that's great news. Who's using 4x? Also good, not too bad. And who's using 3x? Awesome, OK. No raise of hands. That's great, that's good. OK, so that's good because it helps me understand how much of these things you're already familiar with. Hopefully, we do have the slides, and we will try to cover what we're talking about, especially as we have a mixed room. But hopefully, for those of you who are not familiar with traps, you can turn to the person on your left or on your right that raised their hands and also ask them questions after the session. So as we try to make sure that everyone gets to the same page, for some of you, this might be familiar already. For some of you, it might be Chinese. I've tried to think of a language that no one in the room knows. Ended up with Chinese. Apologies for the Chinese speakers. And we will try to make sure that we kind of bring everyone to the same page on how traps can help you protect your endpoints from day one. So let's start with talking about security products in general and what's the difference between capabilities versus policy. So kind of diving deep into, we're all security professionals in the room. Hopefully you are practicing or working around endpoint security. So before we start talking about how to actually protect endpoints and what to protect endpoints from, let's think about the capabilities we have in our organization. And that's relevant for any security product, not just endpoint security. When we think about security products, we have the actual capabilities, the actual things that the product can do, and how it's configured to work, how it's actually doing those things. The way that I like to think about it, it's like looking at the chess tools, the chess actual pawn and queen and so on, and to think about how they can move on the chessboard. That's the capabilities. And the strategy, the policy, is really how you're using them. So your the products you're using are as strong as the combination of these two things, right? Because I can have the best tools available and still in the game. I can still have my queen, but if I don't know how to use it, if I don't have the right strategy, the right policy in place, I might still lose. So when we talk about this today, we'll still talk about kind of the capabilities that you can have, along with the policy, the way that these capabilities are being used. And we'll focus mostly on policy and what's important to have in a policy for that to protect you really from day one. Because it's easy for someone to say, hey, I can teach you how to play chess, really, but it's really not that easy to practice it, right? You don't want a software that you need to actually learn to play chess to figure out how to make the best out of it. You really want the policy to be kind of working out of the box and to have a good security policy. So what makes a good security policy? What actually, we just talked about having the best security policy, but what does it really mean to have a good security policy? So first, obviously we want it to work, right? We want it to prevent attacks by leveraging its capabilities. And we talk about attacks is very general. There are different types of attacks. There are different types of ways of attacks to work. I see some familiar faces of people who were in the session just a few minutes ago. We talked about the difference between malware and exploit and how these things work. We'll dive a bit into that in a second as well, just to make sure we're all on the same page. And we want to be able to do that both for known and unknown attacks. So I don't care if my organization is the first to be attacked. That shouldn't matter to me because I still want it to be as protected as possible. But that, of course, is almost obvious when it's not the first being attacked with a specific malware. So that should work as well. And across multiple phases of the attack. So when we talk about just work, that's what it actually means. Second, especially on the endpoint, especially on users' endpoints, we wanted to have minimal user impact. And again, when we talk about user impact, there are a few things to consider. There's, of course, delays in resource consumption. If it's now hurting my users' capability to actually use their endpoints, it's not a great security product. It's not a great product in general. But it also means that false positives are an issue, and we want to make sure that that's brought to a minimum. And what we mostly want to focus on in this session is to make sure it's on from the start. It doesn't require any specific tunings, especially not tunings that are towards preventing things. We want to make sure, I'm sure you're all very, very smart and qualified in what you do, but I don't expect you, and hopefully other security vendors don't expect you, to work at understanding how attacks work, right? And to understand how different attack vectors work and how different malwares work and what's the behavior they're displaying and what's the characteristics they have. That's why we have researchers for, and that's their job. And we need to make sure we bring that level of knowledge and that level of experience to the products and to make it on from the start, make it as good as possible for as many organizations as possible without you having to say, oh, I also want to prevent this attack, so let's turn this on. But we also understand that what makes sense to one organization doesn't make sense to another, and what may work for 99% of the organizations may still cause issues or problems with that 1%. So we still want it to be flexible to allow you to do modifications as needed in your organization. And of course, we want these two characteristics to continue to be effective as time goes by. So it's great to have a product that works out of the box today, but if it still just has these capabilities 2 years from now, it will get old, it will not be relevant, and it will not be as effective as possible. So we really want this real-time knowledge that our researchers gain with time as they see new attacks, as they see new developments, as they research and find new ways to compromise an endpoint on their own. That knowledge is brought into the product itself. Switching back and forth from kind of the general approach, what we need in general, and how we do that in Traps, let's think about Trapspolicy components. And again, for those of you who are familiar with Traps, this would not be new at all. But for those of you who are new to Traps, who haven't heard about this before, hopefully this will start making sense. So first, we have exploit prevention. Traps, when it started around 6 years ago, was a startup called Savera, actually did only exploit prevention. And the reason we did that is because we believed that this is the most urgent gap that we see in endpoint security. When you think about it back then, malware was even less sophisticated than it is today, but this is mostly what other security vendors did. They had signatures for different types of executables that were causing harm to endpoints. Back then, ransomware wasn't even that common, so it was mostly Trojans or password stealing tools and stuff like that. And no one really focused on exploits and the delivery mechanism to the endpoint itself. So this is really what Traps started out with. But of course, malware prevention was quickly added to the product, as we want to make sure that regardless of how the endpoint is compromised, that would still be prevented. And lastly, so when we talk about malware prevention, we mostly focus here on the behavioral side of malware. Things like ransomware can be prevented if we identify files trying to enumerate over the file system and encrypt files. We can identify different contexts of execution. So PowerShell can be legitimate in one context, but it might not be legitimate in another context. That's the behavior. And on top of that, we have the file examination itself. So not only looking at the behavioral side and the context of execution, but also what the file really is. And again, there are different ways to do this, and we'll dive into each of these components and think about what ways exist, what our approach is to this type of mechanism, and why do we think that's the best approach, both in general, but again, going back to how do we make sure that it's working from day one. You know what, we'll skip this slide just for a second, and we'll start talking about exploits. So one thing, or a few things that are important to understand about exploits. is how they work. Because this is really, for those of us who aren't as familiar with exploits, this is really a very different approach than malware. And the reason that it's a different approach, the reason that it's a different way of thinking, it's a different way of thinking for attackers as well, is that exploits are usually meant to attack applications that weren't meant to run code. So usually when we think about compromising an endpoint, the things that would pop up to mind is delivering an executable, is opening a macro, is running a script. These are all great ways to compromise an endpoint if you're an attacker. But an exploit works in a very different way. An exploit is intended to cause an application that was not meant to run code to actually run code. So an exploit would usually require some software vulnerability. It would start from a bug. It would start from a software not doing something exactly right, not validating the input, not making sure that an object is loaded from the right location. It would start from a vulnerability. If that vulnerability is known, and unfortunately known vulnerabilities obviously exist, whether if it's unpatched or, end-of-life operating system, or just unpatched applications, this still exists, and attackers would leverage this. One example in the latest Google Zero project. It's a group of researchers that do fantastic work in identifying vulnerabilities, but they have a very strict policy. They give the vendor 90 days notice, and if the vendor doesn't fix it in 90 days, they will publish the vulnerability. That's a great way of incentivizing vendors to fix it as soon as possible. But it's also a good way of providing attackers with ideas of how to exploit and how to attack these applications. So these are known vulnerabilities. And there are also zero-day vulnerabilities, vulnerabilities that attackers know about. They found this vulnerability. They're keeping it very, very quiet to make sure they can keep using it, but no one else knows about it. Not the security vendors that can improve their mechanisms to maybe protect against this vulnerability, and not the software vendor that can release a patch and make sure that the vulnerability no longer exists and to be able to compromise. So this is how an exploit starts. The second thing that is important to remember, is that exploits can be delivered in many ways. Browsers are a very common delivery mechanism to exploits. The reason for that is that it's a very complex application that parses multiple types of inputs, multiple types of web pages and objects and so on. So browsers used to be a very common attack vector. We see that trend becoming less and less common. Software vendors, browser vendors, in the last couple of years really did a good work. Even Edge, even Internet Explorer, they really did a good work in making sure that their browsers are no longer as vulnerable as they were prior to that. But we still see that happening very often. So browsers are definitely a relevant attack vector. As they become less common, we see attackers turn to exploiting other mechanisms, other very common mechanisms like Flash that can be rendered within a browser, as well as other applications, Flash objects, PDF files that you can trigger a vulnerability in the PDF reader, and so on and so on. So exploits are very flexible or very varied in the types of files and the types of applications they would require. Usually, though, you would see them in very common applications. You would see them targeting very common applications because leveraging an exploit, leveraging a vulnerability, weaponizing it to an exploit isn't very easy to do. So if I'm already going through the process of actually doing it as an attacker, I would usually prefer doing it for a common application that can allow me to attack as many endpoints as possible. And then lastly, to understand exploits really well or to understand attackers really well, you need to understand what's the process between having that vulnerability. Let's say I heard about it in the Google Zero project, or I know it exists in a no longer supported operating system. But getting from there to an actual code running in a compromised endpoint requires a lot of work. But that work is usually very replicable. It usually is very similar from one vulnerability to another. So you have this bug. You have this, let's say, memory corruption bug, a buffer overflow bug, and you now want to get to code execution on that compromised endpoint. you need to go through several steps, right? You need to get your code to actually reside in the memory of the attacked process. That's one thing. Otherwise, no code of yours will actually exist in the operating system. And again, this is attackers. We're now attackers. And then you actually need to get that code running. So you need to somehow get the application that was supposed to do something else. It's not very interested in running your code, to actually get it to run in memory, or to get it to change its flow to whatever location you put your code in. And these different phases have specific techniques. What we've seen in the last almost decade, since we started researching this, is that there are techniques that occur more and more often, or that occur in most of these types of weaponizations. And there aren't very, very many of those. So there are around 20-something, 25, 28 different techniques that are being leveraged. Some of them are specific to one operating system. Some of them can be replicated across different operating systems, so they can be used both in Windows and Mac and Linux and so on. And by identifying the technique itself, you can actually identify an exploit attempt. So you don't have to understand what the vulnerability is, because sometimes you don't even know about it. If it's a 0-day, you can't really know about it. And you don't have to know the code that will be used when weaponizing that vulnerability. Because if I write the code, or if someone else writes the code, or if some attacker with a hoodie writes that code, it'll be different. So obviously, you don't want to have that be a dependency for whether or not you're preventing this. So this is how exploits work. We'll click all of this just because the graphic, for some reason, skewed for a second. We talked about browsers and the way that they can deliver exploits. One very common technique for attackers to leverage browsers to actually get exploits to run is called exploit kits. So we talked a lot in this conference, in this Ignite, about automation. And this is a very simple way to understand how attackers can automate exploitation attempts to attack as many users as needed. And that can be for a drive-by attack, and really to attack as many users as they can. For example, if they want to run a ransomware or a crypto mining tool, they don't really care who they're attacking. Or it can target a specific website, like the Swift attack example that was mentioned yesterday as well, to maybe attack a specific community, a specific range of users that use a specific website. And this is the way that it works. You need to start from a landing page. You need to have a website to actually go through. Now, that landing page can be something that the attacker created. That can be a whole new website that attackers created. But that's really difficult to get users to, especially if you want large amounts of users. If you want a ransomware that would target as many users as possible, or a crypto mining tool that would target as many users as possible, because the amount of users is proportional, the amount of compromised endpoints is proportional to the gain that the attacker would eventually gain. Creating your own website is tricky. If that website is not familiar, it may not be allowed in specific organizations. Getting users to go to that website, it's not easy. So what you would usually do is to try to compromise an existing website. Now, compromising an existing website, compromising CNN.com, compromising, I don't know which, the rail website, that's not easy. They usually have good security measurements. Maybe that's easy, I don't know. I haven't tried. Usually it's not supposed to be easy. Usually they have good security measurements. They don't allow code to run outside of their organization. So a technique that we see more commonly is malvertising. Malvertising is a combination of malware and advertising. And this is a really interesting technique, because despite of how these websites, despite of how secure these websites are, they still need to make money somehow, right? So usually they will have advertisements. And these advertisements, I don't actually want to change, as the CNN website developer, I don't want to change my website every time an advertiser chooses to change their logo, or every time the ad team tells me I now have a new advertiser. I don't want to do that every time. What I'll actually do is I'll have a server with all the advertisements, and I'll just point to that server. And that will actually fetch a code called iframe. So it's actually code sorry, it's actually input, it's actually data that can run within your browser when you're watching an advertisement. Now, we just talked about exploits and how they work. Once I have something that your browser can render, once I have, in this case, an iframe or whatever type of code it is that your website will render, I now have an opening to try and exploit your website. So this would be the landing page. Again, either a compromised web server, a malvertisement, or an actual web server created by the attacker. And that would be kind of the place where the attack starts, and where users will be they will either decide to go there on their own, or they'll be directed to there using other social engineering mechanisms. Now, once you go to that website, you won't immediately get attacked by this exploit kit. There are two options here. So usually, before the options, usually what the exploit kit will perform is a process called fingerprinting. It will try to understand what's the endpoint, what is the exact information and details about the endpoint that currently access that website. Things like the operating system, the browser version, the Flash player version, and so on, the architecture, and so on, to be able to identify first if it's even possible to attack that endpoint, if it's worth it, and to be able to understand how to attack that exploit. So to attack that endpoint. So the term exploit kit is coined because it doesn't contain only one exploit. Usually they will have a variety of exploits. Some of them are known. Some of them just target unpatched operating system and application. Some of them may be unknown. So that fingerprinting process helps the attacker decide whether and how to attack that specific endpoint. They can decide not to attack it at all. They can decide to attack it with something that is common and known so they don't compromise their own knowledge and capabilities. Or they can decide to actually use a zero-day exploit, which is the most sophisticated type, because it might be worth it or because it doesn't have any other option. So this is what the fingerprinting process is meant for. And then, once they decided to attack the endpoint, they will actually deliver the exploit. So it can be a file embedded in the website. It can be a crafted web traffic. And that's, again, targeted to attack that specific endpoint or that specific, to be more accurate, that specific web browser or applications that the endpoint runs. And that would lead, of course, to the malicious payload. The malicious payload, sometimes called payload, sometimes called shellcode, is usually a very small piece of code that can actually run within that vulnerable application, and that leads to the rest of the attack. So again, thinking about it from the attacker's perspective, if you're exploiting an existing application, that application was not meant to run your code. So it usually doesn't have a lot of space in its memory to contain everything that you want to run as attackers. So attackers would usually create a very small piece of code that's called the payload or the shellcode. And that small piece of code, that shellcode, would be used to then download the ransomware and actually run it, download the crypto mining tool and actually run it, and so on. So that's how the attack actually ends up. So understanding now how exploits work, understanding kind of how the attackers think about it and how exploits actually work, let's think about what we need to have to be able to prevent exploits. And this is really a set of questions more than it is a set of answers. First, we need to think about which processes need to be protected. In your organization, it can be a specific set of processes. Other organizations, it can be another. We talked about attackers trying to attack more common applications, but if they're trying to target a specific organization, they might choose to do something else. And the obvious question that may come up to your minds is, why not protect everything? Why not just protect everything possible? And the reason for that is that there is a cost to any product in protecting an application. And that cost is, of course, even if the resource consumption is low, there is some resource consumption. Even if false positive is to a minimum, there might be some false positives. And some applications are just not worth it. Take the calculator, for example. It's a great application, but it's not likely to be compromised. It doesn't get any external input. It doesn't run very often, and so on and so on. So if I would have chose as which processes to protect, I would probably not choose the calculator, because that would lead, basically any event on my calculator will probably be a false positive event, right? It's not very likely for that to be a targeted application. So that's one thing to consider. The second is an important thing in exploit prevention that we haven't covered yet, is the ability to distinguish between legitimate and malicious flows. Unfortunately, not all program application developers are amazing. And some may write code that may not work as expected. Some code may be old, may be written a while ago, where some programming guidelines were in place and that are no longer relevant, because maybe that's not something that should happen. So it's really important to be able to understand what's malicious and what's benign, what's allowed and what's not. Obviously, as much of this should happen within the endpoint protection software. The mechanisms should be tuned as well as possible to make sure that that distinction is done automatically. But again, that distinction cannot always be done automatically. Some plugins, some external tools, some, as we said, outdated software may still exist. And we need to make sure we have the mechanisms to allow that as well. And then the last question is something we already touched upon, which is who should really tune the policy if there's a conflict? And this is really a good question, which doesn't have kind of a straight answer, because it really depends on what that application is, right? We want to be able to approach something as quickly as possible without relying on someone else, without having to wait for a content update, without having to wait for anything else. But we also want to make sure that if you experience some issue, you won't experience it 6 months later, right? We want to make sure we learn from that. So really want to make sure we have that combination of approaches that allows us to respond to something as quickly as possible without being dependent on anyone else, but to make sure that there is someone or something that collects that data, that collects that information, and makes sure that as a community we learn from previous issues or previous false positives or conflicts that we've seen. So I've shown this slide yesterday as well, so I won't go too much into this, but as I've said, this is something we've been doing for a long time. Even before Palo Alto Networks, this is really what Traps did. It's not, most of it is maybe not exposed in the product, but it's definitely not a checkbox where you can say, hey, I'm doing exploit prevention, and that's it. And it's not something, and it's not something that can be very easily done in the same way that malware prevention is being done. So let's talk about malware prevention now. So this is not lastly. I think the slides are a bit different here. So we talked about file examination and the payload itself. When we talk about file examination and how to identify malicious files on the endpoint, that can be done in various ways and in various times in the lifetime of a file on the endpoint. So first, we need to think about the file types. Again, it's very easy to think about malware as executables, as the only file type that is relevant. But we need to remember, when we talked about this, that multiple file types can be relevant. If it's executables, of course, if it's DLLs, if it's macros within Office files, if it's other script types, all of them can be malicious, and we need to make sure we have mechanisms in place to identify these different file types. We need to think about how the file is being examined. If it's locally or in the cloud, there are combinations of this, and there are reasons to do one over the other. For example, doing something locally means that it can be done even if you're disconnected from the cloud, but it means that you either need to consume a lot of endpoint resources or have a worse result than the cloud. Because obviously, in the cloud, I can do whatever I want. This is our system. We can have something run for an hour and consume 100% of the CPU. That's OK if that's what we decide to do. But if I have something running for an hour and consuming 100% of the CPU on your endpoint, you'd probably not want to buy that product, right? That would be a really bad user experience. So understanding where it should happen, or what's the right combination, what's the right approach of combining these two approaches. And this is what we do. We combine local analysis with cloud analysis, making sure we leverage the right tool whenever possible. And there's also how it's examined. So it can be local, it can be in the cloud, but it can be done in various ways. It could be based on signatures. That has some benefits, don't get me wrong, that's not our approach, but it has some benefits. For example, it's really accurate if you know about the malware and if you know about good files, but it also means that you don't know about anything you haven't seen before, which is obviously not something you would want. It can be machine learning based, again, has its benefits. It can identify things that were never seen before, but it sometimes requires more resources and so on. And it can be dynamic analysis, which means that you have to have the file running, whether if it's in a sandbox on the endpoint or outside the endpoint, or you need to actually have the file running on the endpoint itself. So again, it's not just where the file is examined, it's how the file is examined. And here as well, there is a combination of methods, combinations of techniques that can be leveraged by the vendor, and taking into account the previous topic we talked about, which is the location, there's also a combination of each of these techniques can be leveraged in a different location. So for example, we do have some signatures in the cloud. Even though Traps is not signature-based, Wildfire has signature-based capabilities in the cloud, because in the cloud, that makes more sense. We can maintain databases of millions and millions of signatures, something that we don't want to do on the endpoint. We can update that every 5 minutes, something we don't want to do on the endpoint. So it's not that signatures is bad and machine learning is good, is that we need to consider which type of mechanism we use in each location and why. Dynamic analysis, for example, is another good example, because there are certain types of dynamic analysis, of behavioral analysis, that we can do on the endpoint, but we can't run the file to its completion and only then decide if it's malicious or not, right? If we run it and it's finished running, your endpoint is encrypted. That's it. So there are certain things we are able to do on the endpoint as opposed to the cloud, and it's the balance between the two that is important. Now, I want to dive a bit deeper into machine learning. This will not be a full session around machine learning. We can talk about it for at least a whole session, if not even more. But I do want to talk about what makes machine learning a good machine learning capability. Because again, it's easy to say I have machine learning, but it's not easy from an external perspective, to ask the right questions about how good the machine learning is. So the first thing we need to understand when we think about machine learning capabilities is the data. And really, machine learning can be as good as the data that it relies on to train the machine learning algorithm for. It's the quantity of the data. You can't create a machine learning algorithm based on 10 samples of malware and 10 samples of benign file. It's the variety of data. If I only have benign files that are signed by Microsoft, if that's the only variance that I have, then my machine learning algorithm will learn that Microsoft signature equals a benign file, which is obviously not true. And it's the quality of the data and how well classified it is. So if I have 10 million malware files and 10 million benign files, but I have a 5% error rate, my machine learning will definitely not be better than 5% error rate. It will actually amplify that and would be much, much worse than that. So when you're looking at machine learning capabilities, aside from looking at the bottom line and how good that machine learning capability is, that's something that you would want to ask yourself in how that vendor created their machine learning capability. The second thing is that it needs ongoing training. So we can train a machine learning algorithm today. We can make it the best machine learning capability. We can train it on vast amount of data, really, really well classified data. And today it could be the best. We can test it immediately after. We can create the best machine learning capability. But that machine learning capability might be awesome today. It might not be as good tomorrow, and it will definitely not be as good 6 months from now. Because new samples, new applications, new malware are created all the time. Good applications change, and the way they work change and modify. New sophisticated methods come out every time. So we need to make sure we have that ongoing training, automated ongoing training, to make sure that, that this is kept as good as possible. And this is even something that we do internally, even before we actually have a machine learning product, to make sure that we don't have any biases, any faults within the machine learning algorithm, like the example with the Microsoft signature. We need to make sure we're changing both the data set, the training set, as well as the testing set to make sure we don't have those mistakes within the algorithm. So this is just kind of a quick dive into machine learning. And let's go back and talk about malware. So we talked about the file-based attacks. We talked about, I have a file, I now want to examine it. But obviously, not all attacks starts with a file. I don't always have a file, whether if it's an exploit, whether if it's a fileless attack, whether if it's something that someone missed. It was a file to begin with, and it's now running. There are other mechanisms that need to be put in place before actually allowing or to make sure we're continuing to allow this file to run. So we talked about file-based versus fileless, and it shouldn't matter where the attack started with or what the attack started with. It should be relevant either way. It could be, okay, sorry. And then thinking about the different mechanisms, there are two that I kind of talked about in the beginning and that I want to highlight. The first mechanism, we refer to it as child processes, but really it's how to make sure that legitimate processes are running in a legitimate context. So as you know, attacks are becoming more and more sophisticated, not just in how they leverage different mechanisms like exploitation and so on, but their level of sophistication also goes up by making themselves as similar as possible to legitimate flows within the operating system. So when you think about it, I can be very, very sophisticated and create something that was never seen before to try and attack an endpoint, but if it was never seen before, I can just stop everything that was never seen before, right? So for attackers to gain that additional level of sophistication, for them to make sure that they're not being prevented, they're not being stopped, they can actually make themselves as similar as possible to what users are actually doing on their endpoints. And they're doing that by leveraging legitimate applications, by leveraging legitimate capabilities on the endpoint, and trying to make themselves as similar. So both human as well as software will have a harder time distinguishing between these flows. So one very easy example to think about is process creation within the operating system. And this is the example we're referring to here. As we mentioned before, PowerShell or WScript or other script execution engines, they can be legitimate in your environment. I know they're legitimate in ours. They're used for administrative reasons. They are used, we have obviously lots of developers, so our developers like to automate some of their processes and some of their capabilities, and they use script engines as well. On Mac, Python is becoming more and more common. So we obviously can't blacklist. We can't say, hey, you can't use Python, you can't use PowerShell, you can't use WScript. Good luck with your job. We can't do that. But what we can do is try to identify how that process was executed. If it was executed from an email attachment, that's unlikely to be a legitimate flow. Sure, I can send another developer my script, but that's unlikely to happen. Usually we use code repositories and so on. So a developer will usually run something directly. Another thing that is not relevant, even if there is in this example, there is some users' involvement. But again, we've seen that it's a different user involvement than what we think is legitimate. But another example is that sometimes there's no user involvement in running the script. So for example, if I have a macro that then executes PowerShell, again, that's probably not a legitimate flow in most organizations. So looking at how a legitimate application is created, and even further than that, not just looking at the process that created it, looking at things like the command line, the user, and so on, helps us understand the context of execution better and helps us make sure that we can better distinguish between those legitimate flows that we don't want to block, we want to allow in the organization. At the end of the day, that's what we need to make sure of, but we also want to make sure that they are distinguished. Another type of behavior we can talk about is ransomware-like behavior. And again, I gave this example before. This is a great example where we look at the intent of the execution and not the file itself. So it can be any file. It can be a file type we may not even look at. It can be a new file type that we haven't thought about looking at. But at the end of the day, there's some code in the operating system that goes and tries to encrypt files. And that's a very common behavior to two types of application, either ransomware or legitimate applications that can somehow modify or encrypt the disk. And it's important to distinguish between the two, but even if we don't, even if we just look at this behavior as a malicious behavior, that's something that, again, ransomware may display very often and something we want to continue to monitor. So the bottom line of this is that you want to make sure that the attack vector, the exploit, or the delivery mechanism, like the macro, is prevented. But you also want to make sure that you have a mechanism in place that continues to examine the file's behavior and the operating system's behavior, even after that initial scan or initial execution, to make sure that these behaviors are not displayed. And I want to take you through an example. So we talked about exploit kits. And the first example we'll talk about is the rig exploit kit. The rig exploit kit actually exists for a very long time now. It exists for about 4 years, 5 years almost. And as I said, it's an exploit kit. So it includes several exploits. Those exploits can change over time. And what's interesting about the rig exploit kit is that its final goal was actually changed as well. So it's actually, in the attackers community, in the attackers ecosystem, it's actually a service. I can create an exploit kit, you can create a malware, and then you can come to me and say, hey, I want to use this exploit kit service you provide in order for my malware to be distributed. So this is really an interesting ecosystem. And from the exploit kit side, obviously what they're in charge of is to make sure they're compromising a website. They then perform the fingerprinting to make sure that that they don't compromise and don't try to attack an endpoint that should not be attacked. And then they provide the malformed payload. In most cases, the rig exploit kit actually focuses on Flash in a lot of cases. They do have some other things, but they focus on Flash very significantly. And that would deliver the malicious executable. So this will actually be the handoff between the malware developer and the exploit kit provider, if you want. And that will, of course, lead to the eventual goal of encrypting the endpoint. Now, we talked about traps, or the mechanisms, our approaches, for quite a while now. You're probably wondering, so how will it work here? How will it be prevented? So we talked about the different techniques that attackers can need to leverage to actually compromise an endpoint. The first one being the fingerprinting, which can be prevented by traps, by identifying that fingerprinting technique. The malformed payload is, of course, exploiting a memory corruption vulnerability within Flash, can also be prevented by traps. And then the malicious payload will immediately be examined using our file examination capabilities to make sure that it's not known to wildfire as a malicious file. For those of you taking screenshots, this is not the end. To make sure that it's if it's known to wildfire, then we can prevent it. But if it's unknown, we'll examine it using our behavioral and our static machine learning capabilities. But then, of course, we will also examine it using our behavioral mechanisms. So this is a really good example where you see all those different mechanisms working within the same attack. Hopefully, the first one will be enough, and this will be prevented. But we do understand that attacks and attackers evolve, and if they change 1 or 2 building blocks, this will still be prevented. So this is a really good example of the combination of all these types of attacks. And we haven't dived too deeply into this because we have talked about how exploit kits work. So this is really just to show you an example for that. An additional campaign that I want to talk about is the dog call campaign. This time it actually starts with an Excel document. And that Excel document actually contains an embedded encrypted Flash file. So Office applications tend to be very open in the objects that they can integrate with. And Flash files can be embedded within Office documents to provide animations. So in this case, it actually contains an embedded encrypted, or part of the Adobe Flash file is encrypted. To open the encryption, it actually goes to a remote server to request the key, and then uses this key to decrypt the rest of the Flash file. The rest of the Flash file actually contains the zero-day exploit. And that exploit will then trigger the malicious payload, which is dog call, which is actually a rootkit. So previously we talked about coin mining and ransomware. This is a much more sophisticated attack because at the end of the attack there's an actual Trojan. So it means that it's not, let's send it to everyone and get as much ransomware money or as much coin mined as possible. This is actually where the output, the data collected from this rootkit, is actually relevant for the attackers. They want to collect passwords, they want to be able to connect it back to a CNC server, and so on. So a much more sophisticated attack. And that level of sophistication should also be triggered for you when you see the encryption mechanism. Because this exploit was actually, until this attack was found, this was a zero-day exploit. So attackers wanted to make sure in this phase, in the second phase, they wanted to make sure that they're not compromising their zero-day exploit for machines that cannot be attacked with this exploit, or for machines that might be investigated later on. So it's not a VM. It makes sure it's not a VM. It makes sure all sorts of similar things before it actually decrypts the zero-day exploit. So in case this falls into the wrong hands, it will be very hard to actually analyze and find the zero-day exploit, and they can continue to use it. So a very sophisticated attack. And again, we see a combination of two prevention mechanisms. First, the exploit side, which was prevented by traps even when it was a zero-day, as well as the rootkit itself. And then the last campaign that I want to talk about, and hopefully this starts to be a bit repetitive because we can see that the techniques that attackers are using are similar. So it's not repetitive just because we want it to be. It's actually real campaigns, all from the last year. I didn't mention this, all from 2018, that we're actually seeing in the wild. So this campaign is actually a group called Sotacy. We don't know who they are, but some researchers suspect that they are connected to the Russian intelligence forces. So really, again, a very high level of sophistication. And this attack, again, starts with an Excel file. But this Excel file does something very different. This Excel file actually contains an embedded executable payload. The embedded executable payload is actually text. It's actually base64 encoded text within the file itself. If you scroll all the way down to line 2,700 and something, you actually see a blurb that if you decode it using base64, it's actually an executable. And this macro-enabled document, the macro, what it does is to actually run something called certutil. Certutil is a built-in application in your Windows operating system that is usually used to handle certificates. That's where the name comes from, certificate utility. And one of the capabilities that it has is to decrypt the certificate, right? You need to decrypt the signer to make sure that the certificate is valid. So they're using this tool, the certutil tool, to actually decrypt their own payload. So up until now, there's nothing actually out of the ordinary that is running within your operating system. Two legitimate applications, Word and certutil, obviously signed by Microsoft, so can't be a non-legitimate application. But then it runs an executable. That's the decoded executable. That has another level of embedded DLL. That's another level of embedding a payload within that executable. And that DLL is what researchers refer to as the Sotacy Campaign Trojan. And this Trojan is not only a really bad Trojan, it can take screenshots, could use the camera, microphone, and collect data, and so on. It also has a persistency mechanism. So even after you finished opening this file, you noticed something is wrong, you click close. This process takes milliseconds to happen. You already have a Trojan on your endpoint with a persistency mechanism. And just to show you how this looks like, this is actually an animation of what happens when you click Enable Content up on top. Now, again, I said this is a very sophisticated group. This content actually makes sense. It targets government and military organizations. So I'm sorry for the back and forth, but it actually contains real information about conferences related to government and military organizations, things like armed vehicles and maritime reconnaissance and stuff like that. So you really see the level of work that went into making sure this looks valid. And users are likely, with this level of content, are likely to keep scrolling and looking at the document and actually letting the document run even after they enable the content. And this is the embedded shellcode. So you can see I scrolled all the way down to line 2227, so unlikely for someone to actually scroll all the way down. And this is actually, if you just copy this and decode this, base64, this is an actual executable. So very, very interesting to see the combination of techniques that were used by these attackers. You can see here they're not reaching out to any external server to get that executable. They want to make sure that everything happens on the endpoint. And they have these checks in place, again, to make sure they're only continuing to leverage this attack if this endpoint is specifically interesting, because it's, again, not a drive-by attack. It's a targeted attack for these types of organizations. And of course, lastly, we want to understand how traps could prevent this. So the macro will be examined by traps. That's obvious almost. What should be obvious by now is that the search util running from Excel, even though it's legitimate, we talked about the context of execution, will be prevented as well. And then, of course, the malicious executable and the malicious DLL. So this is really not about new techniques. This is really about the context of execution and to show you the level of sophistication here. And then lastly, I know we're out of time, but I also wanted to talk about the process of updating the policy. And this is something we want to make sure that our researchers are doing on a constant basis, on a continuous basis, collecting the input, modifying the policy, reviewing and testing it, and making sure to distribute it back again, both to learn from our customers and make sure that if one customer experienced something, another wouldn't, as well as to learn from attacks and new mechanisms that attackers leverage. So with that in mind, I think we can skip the rest of it. I don't have a way to skip the rest of it, but it's summarizing everything we talked about. I know we're out of time, and I'm sure you have other sessions. So if you have questions, I'm here. I'm more than happy to answer them. For those of you who already have to rush out to your to the rest of the day, that's completely fine. Thank you so much for being here and for your attention. Thank you. That's it. Email. This is not my email. I don't know who this email is.